In electromagnetic spectrum, we have various radiations or rays, that is gamma rays, X-rays, the UV visible region, the IR, microwaves, and radio waves. So we are going to concentrate on the UV and visible region. The UV visible region roughly consists of 10 nanometer to 800 nanometer. Where exactly 10 nanometer to 100 nanometer, we say it as an extreme region in the UV region, extreme rays of the UV region, because it consists of the shorter wavelength and higher frequency. Where 100 to 400 nanometers subcategorized into UVA, UVB, UVC, and UVV. Again, the UVV is also usually not present in the laboratory equipment, that is 100 to 200 nanometer. So our range in the laboratory equipment consists from the 200 nanometer to 800 nanometer. So if we see the normal spectroscopy, it consists from the roughly from 150 nanometer to 800 nanometer, or 200 to 800 nanometer. So this UV spectroscopy follows the Beer-Lambert's law. And what exactly is the Beer-Lambert's law? Beer-Lambert's law consists of Beer's law and Lambert's law, where exactly Beer's law says that the amount of light which is absorbed by the solute is directly proportional to the concentration of the solute in the solution. So let's say if you have a iron in a solution, you want to estimate it. The concentration of iron is directly proportional to its absorbance, or absorbance is directly proportional to the concentration of the ion present in that particular solution. So that means A is equal to ASC. So A stands for the absorbance of the test, A stands for the absorbance index. The absorbance index is nothing but a capacity of a solute to absorb that light of the wavelength. And the C stands for the concentration of solution. So let's go to the Lambert's law. The Lambert's law states that the amount of light absorbed is directly proportional to the length and thickness of the solution under analysis. Now here, length and thickness, we speak in terms of the cuvette. The cuvette which we use for the sample holder in the colorimeter or the spectrophotometer. The thickness of it and the length of it is directly proportional to the absorbance. So absorbance is directly proportional to the length and thickness of the cuvette. So that is A is equal to AS and B. That is given here. So A again stands for the absorbance of the test. That is nothing but the analyte or the solute, the absorbance index, and then B is the length or thickness of the solution. So we combine these two laws and have Beer-Lambert's law. So Beer-Lambert's law, totally we say it as amount of light absorbed by the color solution is directly proportional to the concentration of the solution and the length of the light path through the solution. So here we are saying absorbance is directly proportional to the concentration of the solute in the solution, at the same time the length or the thickness of the holder. So that is what. So this at the end gives the A is equal to epsilon naught Cl as the final formula of the Beer-Lambert's law. So A stands for the absorbance or the optical density. C is the concentration of the solution. L is the path length, and epsilon is the absorption coefficient. So this is what exactly the Beer-Lambert's law holds. Now, when we speak about the UV visible spectrophotometry, we have to speak about the UV region as well as the visible region. Visible region solution usually are colored. That means if you want to analyze the glucose, estimate the glucose, you make sure that glucose has reacted with the reagent and given the color which you are able to analyze through the colorimeter or the visible region wavelength. So here in the UV region, it is not necessarily a compound which is analyzed to be colored, which cannot be, even without the color, it can be analyzed. So what exactly we hold here? What is exactly the phenomenon? What is exactly the matter which is able to analyze through this component? So, what exactly are the factors influencing the absorbance of the UV light by a compound or analyte? So, we will go through it now. Now, as I said, the UV light ranges from 10 to 400 nanometer, but usually the laboratory equipments are from 150 nanometer to 400 nanometer. So, not all the compounds are able to be absorb UV light. That means all the molecules